This machine is turning at just over 107 revolutions per minute, but somehow it is producing electricity at 50 Hz. And that's not even the strangest question you have been asking me. How can a wicket kit be 110% open? How does a generator this massive actually synchronize with the grid? What happens if someone accidentally opens a wall while you are inside? And why do some of these machines sound like they are about to tear themselves apart? So today I'm answering some of the best questions you have left in the comments. I've been reading through your comments, and honestly, some of you are asking questions that even engineers would stop and think about. So instead of answering them one by one in the comments, I have picked some of the most interesting ones and brought them into one video. And we are starting with probably the biggest mystery, 107 RPM. A lot of you noticed something interesting in one of my videos. I mentioned that this turbine is running at 107 RPM. But if you look at the technical specification, the actual rated speed is 107.14 RPM. I simply rounded it to 107 RPM when I was talking about it. The formula to calculate frequency is number of poles times RPM over 120. For this generator, the number of pole is 56 and the actual rated speed is 107.14 RPM. So 56 times 107.14 over 120 is equal to 50 Hz. Now compare that with the high-speed Pelton turbine. This Pelton unit runs at 600 RPM. So the generator only needs 10 poles to produce the same 50 Hz frequency. But this is a low head Francis turbine. Its rotation speed is much lower. So the generator uses a much larger number of poles. And because the head here is relatively low at around 100 meters, the turbine needs a much larger flow of water to produce the required power. That is why these machines are physically enormous. Instead of spinning extremely fast, they use a large number of magnetic poles and operate at relatively low rotation speed. It may seem that this unit is not spinning fast. That is actually the point. The machine doesn't need to spin thousands of revolutions per minute. Its large number of magnetic poles allow it to generate the required 50 Hz electricity at a much lower rotational speed. And just to clear up one thing, when I said 107 RPM in the previous video, I wasn't saying the technical specification was exactly 107.000 RPM. This one is a great question. Because if a door is fully open, how exactly can you open it another 10%? The most important thing is the number you are saying is actually not a measurement of physical distance. The governor opening signal is normally based on calibrated reference or rated position. Think of 100% as the plant defined full open reference. A value above that can represent an extended control range, calibration reference, or a position beyond the nominal rated point, depending on the specific governor and instrumentation. So when you see 110%, don't imagine the gate somehow becomes bigger. The number is telling the control system where the gate is relative to its defined reference. In other words, the gate didn't break the laws of physics. The percentage scale is what changed. Now let's imagine the turbine is starting from zero. The water starts moving the turbine accelerates, the generator starts producing voltage. But there is one problem, the grid is already running at 50 Hz. You can't simply connect your generator whenever you feel like it. Before the generator breaker closes, the generator has to match the grid condition closely enough for synchronization. The turbine governor controls the mechanical input and therefore the speed. The excitation system controls the generator's magnetic field and voltage. And synchronization equipment checks the relationship between the generator and the grid. The goal is simple: get the generator spinning at the correct speed, get the voltage right, and get the phase angle aligned. Then the breaker closes. And suddenly this massive machine becomes part of the electrical grid. After synchronization, the generator doesn't just freely speed up or slow down like an isolated machine. The grid effectively holds it at the synchronous electrical condition. From there, changing the turbine mechanical input mainly changes the power being delivered to the grid. Now, let's get to the question that probably made the most people uncomfortable. First, this is exactly why hydroelectric facilities have strict isolation and safety procedures. Before people enter certain areas of a water conveyance system, the relative equipment has to be isolated. Depending on the system, this can involve closing walls or gate, electrical isolation, hydraulic isolation, draining or depressurizing sections, and applying lockout, tagout procedures. And the important word here is verify. You don't simply assume that a valve is closed because the control panel says it is. The condition has to be verified according to the plant safety procedure. Because when you are standing inside a water passage designed to move hundreds of cubic meters of water, you don't want to discover that something wasn't isolated properly. The most important piece of equipment inside a hydro plant is not always a turbine or a generator. Sometimes it is the procedure that makes sure nobody gets hurt. Another question I get all the time is about the sound. Some of you say this sound is amazing, some say it sounds like a machine from a nightmare, and here's something important. Not every strange sound means the turbine is filling. Inside a hydro unit, you are hearing a combination of water flow, mechanical vibrations, rotating equipment, hydraulic effects, and electromagnetic forces. And sometimes that sound, like sand or gravel, can actually be related to cavitation. Cavitation occurs when a local pressure drops enough for vapor bubbles to form and then collapse. That collapse can create noise, vibration, and eventually damage if the condition is severe. So when you hear that strange crackling or rumbling sound, you are not necessarily listening to sand hitting the turbine. Sometimes you are listening to water behaving in a very violent way. A lot of you ask me where these locations are. Some are obvious from the footage, some aren't. And sometimes I don't reveal every detail because the footage is about the engineering rather than the location. The sirens aren't just there for dramatic effect. There is a part of warning system used to alert people that conditions downstreams are around the structure are changing. And yes, they make the footage much more dramatic. But that is not why they are there. Some of you also asked why I sometimes say 6 feet instead of meters. Simply, the people may use one measurement system while the audience uses another. For the videos, I will try to give you both whenever the measurements actually matter. Because the important question is not whether we call it feet or meters. It is how much water is actually moving. And that's actually what I love about these questions. At first glance, you see a giant turbine, a giant gate, a huge dam, but behind every number on a display there is an engineering reason. 107.14 RPM is not just a number. 110% is not just a number. A synchronization button is not just a button, and that terrifying sound is not necessarily just noise. Every one of these things tell us something about what is happening inside the machine. So keep the questions coming, because some of the best videos on hydro vision are not the ones I planned myself. They are the ones you force me to investigate. If you have a question about turbine generators, dams, gates, governors, synchronization, or anything else you have seen on this channel, put it in the comments. And if enough of you ask the same question, it might become the next Hydrovision investigations.